So, we have seen application, or we have seen in theory the analog to digital converters and digital to analog converters, right. So, let us now see how we can implement this digital to analog converters using the TI board, and we will also see one or two applications of this particular DACs. Right. We have seen or we will be looking at one of the experiments where we will be looking at flash ADCs and how you can implement this using the breadboard, but here we are talking about DAC and we will be using this DAC using the TI board. Now, TI board you already have seen in earlier classes, so it is kind of easier for you to understand how to use it, and the idea is that if you know how to implement the DAC, you should also know what are the applications of DAC. So, to make sure that once you know how to implement this, we will also show you what are the applications. So, let us see in the following sections as an experimental class how you can implement digital to analog converter.
In the past few short modules, we had seen the ASLK or the TI analog systems lab kit board that we are using as a tool in this course to familiarize you with different analog design aspects that you need to be aware of while doing analog circuits. As you are well aware, like analog design is a very challenging task. So, and the several constraints that you need to take into account are plenty, which we will be taking you through to during the duration of this course. So, we had covered many parts of this board. So, the intention of covering different parts of the board was not to just tell you how this board works, but generally how PCBs should be designed, how a development kit looks like, and how to best use a development kit to make for your own understanding of the whole engineering or the concepts involved, but it is not necessarily to make you acquainted with this specific board. The board is just a tool. So, we had covered many parts of the board like the power supply unit, the multipliers, a few parts of the multipliers, and the different what do you call inverting and non-inverting configurations, all those in the board. So, another major part in the board, in the analog systems, what is the board? It is analog systems lab kit, ASLK, that is supplied by Texas Instruments. So, that is just we have just used that board as just a tool to keep you acquainted with the analog design aspects. Okay. So, that is the tool, analog systems lab kit. So, today we will be seeing the very important, a very interesting actually part of the board, which is the digital to analog converter, DAC. What it is? Digital to analog converter. So, this is what, so the lab has a dedicated digital to analog converter board. That we will see, we will power on the board and give inputs to it, and see how for different digital inputs what are the analog signals generated. But before we delve into it, you might have covered it in previous courses or in your maybe in your engineering course, if you are an engineering graduate who is taking this course, or you might also have come across this during this course. You have come across this during the duration of this course also. But before you can understand you see the beauty of how the circuit is working in the board, we need to just refresh our own knowledge about how digital to analog converters work. So, we will go through the basic concepts, and I will go through it in a very, very fundamental way. No formulas no formulas, just a brief concept in such a way that at in every point later in your life you will never have to think again how digital to analog converter works and how analog to digital converter works. So, for many people in the industry, or who have lost touch with their core engineering education after working for so many years, and even engineering students who are doing it sometimes have to think at least for like 1 or 2 minutes exactly, okay, DAC, ADC. They get slightly confused. They know it's inside them, but then they get slightly confused about, okay, what is the difference between ADC, DAC, what exactly was the difference. But this is mainly because of the methodology we use to understand these concepts. because sadly engineering education in our country most of the times we try to, or the way we have brought up in our schools, we try to learn the formula of the conversion not without necessarily understanding exactly what is happening inside. So because of that, we just when we are our mind is also like a memory. So when we are suddenly asked what is DAC or what is ADC, we will just try to access the formula that is stored in our mind instead of just understanding or trying to recollect what exactly the concept was. So if you fully take in the concept, then you would not have to actually think how it is, it will automatically come to you. So the intention of this short module is also to introduce you to how to imbibe a concept in such a way that you do not have to make a concerted effort or a conscious effort to recollect its basic fundamentals. So that is the idea. So with this backdrop or philosophical idea in mind, let us see how a digital to analog converter or even an analog to digital converter, because these are like two sides of the same coin, you might have heard, right, two sides of the same coin. So we can at one shot when we are refreshing, we can refresh both digital to analog converters and analog to digital converters. Okay. So let us get started with the basic concept building. Okay. So before you start, you should always, the only thing that you should remember is that for any conversion, for an analog to digital converter or to your digital to analog converter, you will have your base voltage, which is usually 0 volt, and you will have your maximum voltage, which is usually your supply voltage, let us say 15 volt or 10 volt or 5 volt, whatever it is. The supply voltage or the VSS would be the power supply that is available to your board or to your design. Okay. Usually your converters are operated in this range, fine. So these values, so from 0 to 15, so if you see that how many values are there from 0 to 15, yes, you guessed it correct, there are infinite values from 0 to 15 volt, and that is why it is called analog signal. What is analog signal? Analog signal is that if you try to look at a signal, the signal can take any value from its set lower and upper values, correct. 15 volt if you set, so let us say you set 15 volt here and 0 volt here, in the duration of time this signal can take any value. Okay. This is an analog signal, correct. Whereas a digital signal translates, it is like it is quantized. Okay. What is digital signal? A digital signal was fundamentally invented. So you should also understand why was digital signal invented. So digital signal was fundamentally invented for two main things. One is for computational purposes, because as you will all be well aware that digital signals play with only zeros or ones, either 0 or 1. So for a computation or a processing perspective, this is much easier than being than the need to process so many signals here in analog. So a digital signal has only 0 or 1, correct. But then what does 1 mean? Does 1 mean that it is 1 volt? Does it mean that? No, it does not mean that. And 0 also may not necessarily mean 0 volt. It depends on what is the thresholds you set. So this is something that you should understand fundamentally before you even look at what digital to analog conversion and analog to digital conversion is. So let us say we have again that we have 0 to 15 volt as the range of values that your system or your board or your circuit has an input. So in digital domain, if you call in digital domain, what we do is that we will set a threshold value. This is a very crude way I am telling you, this is not exactly how things are implemented in products, but this is how you should understand things so that it all comes to you naturally. So you keep a threshold voltage, let us say VTH, okay, and you would say that if the input voltage, signal input voltage is below this value, okay, then I will consider all these values as 0 volt, and if the input voltage is above this value, we will consider it as 1 volt. Okay, fine. So then we have this is what we call it as quantization. We have quantized the whole range of infinite, even this this interval, right, even this interval is has infinite values, correct. It can take up to however decimal places we want. So this infinite band of voltages, by setting this threshold voltage of VTH, we are quantizing that it will be 0 volt. And this band of voltages, let us say this is 7.5 volt midpoint. So we say that if voltage V in is anywhere between 0, V in is greater than or equal to 0 volt, and so let me rub this off. I think this is clear to you, we will come back to this. If it is anywhere between 0 volt and less than 7.5 volt, let my system translate it to a digital binary value of 0. We do not call it 0 volt, it is just 0, it is binary 0. So, it is binary. Okay. Now, let us say now if V in is such that V in is greater than or equal to 7.5 volt, okay, and less than or equal to 15 volt, we will translate it to binary 1. Cool. So, this is a fundamental idea, correct. This is how binary 0 and binary 1 would be defined when you start off with the concept of digital logic, but there are issues in this, we will come to that. Just let me reiterate it once again, I think it was not written clearly. So, a binary zero would be V in greater than or equal to 0 and less than 7.5 volt. This is also 0 volt. Even if it is 0, you have to write it as 0 volt, please make sure that also. These are all conventions that you need to follow, this gives professionalism to whatever you do. So, let us say we have binary 1, so that will be V in would be greater than or equal to 7.5 volt and less than or equal to 15 volt. If you notice clearly, if you have the eye for detail, you will notice that here this is less than 7.5 and here only we have put the equal to sign. So, that means if the V in value is 7.5, let us say, then we will translate it to a binary value of 1. Okay. So, this is like the crude way of how analog to digital conversion would be done, but then this has its limitations. What are the limitations? So, the limitation is that we are setting a very fine threshold here, and let us say your input voltage is 7.49. Let us say your input voltage is 7.49, then as per our logic we will translate it to 0, right, but let us say your input voltage is 7.51, we will translate it to 1. So, what happened with a voltage change of 0.02 volt, okay, you translated from a binary 0 to binary 1, which is a very huge change in the digital domain. So, what does this mean? What does this mean? So, what happened now? Let us go over it again, I think we were a bit fast there. So, let us say our input voltage was 7.49 volt, that as per our logic we translate it into binary 0. Okay. Now, after some time our input voltage became 7.51 volt, but as per our logic we translate it to 1. So, for a change, so this is one voltage, say let us say this is V1 and this is another voltage, let us say this is V2. Okay. For a voltage change of V1 minus V2 equal to how much? 7.51 minus 7.49 volt, which is equal to 0.02 volt, we got a digital logic change from 0 to 1, correct. So, this is very dangerous from a circuit design point of view, Can you tell me why? It is a very important concept in all design. Can you think of why this would be the reason? Yes, you guessed it correct. In all our discussion, we looked at the ideal scenario, a noise free environment, everything. But then all circuits, all our systems in real world will have a big enemy called noise. There are people doing PhD in how to reduce noise. So, noise is a very important constraint in digital design, analog design, in whatever electronic circuit design we do. Noise comes in circuit design, let us say analog, digital, and also mixed signal design, which is where both comes. Noise is an important parameter in communication systems, because we have to take into account the noise level and the noise background in our communication channel. Okay. Noise is an important concept in signal processing. Okay. What other domain of electronics do you think is there? Actually, noise is there in everything that you study in electronics and electrical. Noise is there in power supply. If you are designing power supplies, there also noise comes. Noise is there in communication systems, noise there in signal processing, noise there in circuit design, noise is there in information theory, which is a part of communication systems. You have heard of Shannon's bandwidth, the famous bandwidth formula. Everything has the connotation of noise in it. Okay, if you think about it, you can find lot of other places where noise plays a pivotal role. Okay. Now let us come back to it. So we found out that for a 0.02 voltage change, we got a transition from binary 0 to binary 1, correct? Yeah, we got a transition from binary 0 to binary 1. So this is so we have seen that this is a practical module in this course. So our idea is to look at it from the practical point of view. The theory part is also anyway covered. So that's why we are not looking into formulas or anything. We are just looking at like a hands-on point of view, correct? So for a 0.02 volt transition, 0.02 volt transition, we got a transition from 0 to 1, correct? That is very clear. Now the problem is, okay, now it will be very clear to you. The problem is that let us say the base voltage was 7.49, but there was a noise component of 0.05 volt noise in your signal, then it could always fluctuate between above 7.5 and below 7.5, correct? Then the conversion to digital would always fluctuate between 0, 1, 0, 1, 1, 1, 0, like that. Okay. Depending on what is the value of noise at that point of time. Noise is a random signal, that is generated from a random process. So you can never predict what the value of noise would be, noise voltage would be at any given point of time. So because of that, you need to set the threshold within a window, and then that is why we have something called VIL, VIH, VOL and VOH. So these are very different concepts in digital design called V input low, V input high, V output low and V output high. So I will not get into the full details of this because this is actually not part of an analog design course, but the idea is that you will not put this single threshold like this and tell that anything below this will be 0 and anything above this will be 1. What you will do is that you will have a threshold below and tell that if your voltage is somewhere below this, okay, then only you will take it as 0, and if your voltage is above this point you will take it as 1. So, this is like kind of like no man's territory, no man's land. So, your 1 is clearly defined much above and your 0 is clearly defined much below, and this is the buffer that you keep for your noise. This is a crude way of looking at it. There are detailed discussions on this in digital design. Okay. Now, let us get back to our idea of how to understand intuitively, because this is a practical session, intuitively of how digital to analog conversion and analog to digital conversion is done. So, where did we start? We started that there will be a peak voltage, let us say VSS, that could be 15 volt, 10 volt or any voltage, 5 volt, anything, etc. You have the floor voltage, that is 0. Okay. So, the range of values here represents the analog domain. Okay, represents the analog domain. Now, what in analog to digital conversion, what we do is that we will discretize, what is called discretize. We will discretize the number of values that the input signal can take from this infinite spectrum of voltage values. Okay. So, what it means is that we will divide this simple English, in simple logic ways, in logic term. What this means is that we will divide this whole range into definite number of intervals. Okay. We will divide it into definite number of intervals. So, what it means, let us say we need 10 intervals like this. Okay. Then what it means, so I need 15 volt minus 0 volt by 10 intervals equal to what, 15 by 10 equal to 1.5 volt. So, 1.5 volt is my interval value. So, that what does this mean? So, this will be 0, my first level will be 1.5 volt, my next level will be plus 1.5, so 3 volt, my next level will be 4.5 volt, then 6 volt, 7.5 volt, 9 volt, okay, then what, 10.5 volt, like that you will go, we will have 10 levels. So, this is 1, 2, 3, 4, 5, 6, 7, like that up to 10 we will have. Okay. These are the levels that will be there, correct. So, there are 10 levels, but usually as you will be aware, the digital signals are binary, right. So, depending on the number of levels that you need, so each level, so you have fixed the levels right here. So, each level then we will represent by a sequence of binary digits like 0 0 1 1 0 0. Okay. Now, the number of digits, number of places that will be there in this digital representation, what does it depend on? Now, it will be very clear to you. Now, it is very clear to you that this depends on the number of levels itself that you want to have, and because we are dealing with binary, that is 0 or 1, the base is 2 and the base is not 10. Your normal digital numbers from your normal decimal numbers from 0 to 10 has base 10, correct, base is 10. Okay. But because now in the digital domain, binary domain, what is called binary, in the binary domain you have only 0 and 1. So, the base is 2. That means what? That means that you have, what does base mean? Base means the number of unique representations that are there in your number system. So, because this is 0 1, correct, the base is 2. What does hexadecimal mean? Hexadecimal means 1 2 3, like that we will go up to 9, then we will have A, B, C, D, E, F. We have total 16 unique representations, correct. So, that is hexadecimal system. So, the base is 16, correct, the base is 16. Same way we have octal system. What in octal system, what does it mean? Octal system is you have up to 1 to 7 and the base will be 1 to 7, 0 to 7, sorry, 0 to 7 and the base would be 8, correct. Okay. So the base also represents what is the packing density of information that you can have. So let us not get into those things. So what did we understand now? The number of digits that will be there in your decimal representation, this is your decimal domain, sorry, digital domain, not decimal, that will be there in your digital domain, this is your digital domain. So number of digits that will be there in a digital representation depends on the number of levels that you want to fix in your analog domain. So this is how you travel from your analog domain to your digital domain. Okay. So now what is there? So because it is by the base is 2, it is always good to have, so base is 2, right. So base is 2. Now for us to use the number of digits, say let us say the digits are 3, correct. Let me wipe this out fully for your clarity. And I will put the levels clearly on one side so that you do not get confused. Okay. So we have your VSS 0 volt. Okay. So we have understood that we will have to fix definite levels here, clear. Now we told that there will be certain digits, number of digits 001, 101, etc. Okay. And we also told that the number of digits, like number of places or number of bits, I did not want to introduce the concept, but number of bits that will be there in the digital representation of your analog level. So this is your analog level. These are simple terms that you need to use, I mean, or you need to understand, and it will come to you automatically once you understand this thing. So this is the analog level, right. So this is your digital representation. This is a digital representation of your analog level, correct. So the number of digits in your digital representation depends on the number of analog levels that you need to use. So that is very clear to you, that would come clear to you. Now we have also seen that the base is what? Base is 2. Now for us to use all the digits with full efficiency, let us say we have 3 digits here, for us to use digits with full efficiency, we need the number of levels that we divide our analog domain into should be a multiple of 2. Okay, multiple of 2. So what does this mean? That means that let us say your number of levels is 8. Okay. So what is 8? 8 is 2 raised to 3, correct. So it is a multiple of 2. So how does that, how it helps is, it will help you to use all the bits with all the toggles. So if it is, so this 3 represents the number of bits that will be there in your digital representation, correct. So you will start off with 0 0 0, that will correspond to 0 volt. Then you will have 0 0 1, then you will have 0 1 0, then you will have 0 1 1, like that 1 0 0, 1 0 1, 1 1 0 and 1 1 1. So you have 1 2 3 4 5 6 7 8. So you have 8 levels. This is this, clear. Now what you observe? So each bit has toggled from 0 to 1 throughout, and all the bits have been fully used. What does it mean is that there is no other combination of changes possible for these 3 bits. That means whatever combination of zeros and ones we can make out of these 3 bits we have made by making use of 8 levels. So if you are designing a system, that means that we have used the bits to its complete efficiency. Okay, eta. we have used the bits to its complete efficiency. So that is why, so we can also always have, let us say, only 5 levels and we will use 3 bits. So that means that we will only use these 5 levels here, or maybe select 5 levels from here and other bits will not get used. So that is not a very good way of designing circuits. So that is why we always go for a multiple of 2, because it is a binary system. We always go for a multiple of 2 levels in your analog domain. So now that is clear to you. So what have we done now? We have discretized your analog signal and into a series of digital bits and then set their values, like what defines them at what point. So what have we necessarily done? We have necessarily done what is called analog to digital conversion. So what this means is that we have 0 to, let us say, 15 volt. Let us stick with 3 bits now. That means we will have 8 levels, right, as we discussed, correct. So that means 15 volt minus 0 volt by 8, okay. So 15 by 8, it roughly comes to around 1.98 volt. Roughly comes to around 1.98 volt, roughly. I have not calculated, I am just telling you. So your first bit, so your base 0 volt will be your first digital representation 0 0 0, okay, and your next one will be what, plus 1.98 volt. So 1.98 volt would be 0 0 1. So this is what we call the least significant bit or LSB, and this is what you call your most significant bit or MSB. Clear? This also you must have learned, but do you know why it is called so? Do you know why LSB is called so, that it is least significant bit, and why MSB is called most significant bit? We will come to that. It is an important concept that you should understand. You should whatever. So another main thing in engineering education or whatever education is that you should be very sure of whatever terms you use. You should never be doubtful about the meaning and full understanding about whatever technical terms you use. If you don't know it, we should not use it, but if you know it, we should know fully why it is called, why each thing is called so, okay. So this is MSB and this is LSB, okay, and this is MSB, correct. We will see why that is called so. So we understood that. So this will be like 1.98 into 3, like let us say this is around 2 volt, this will become 4 volt and that will become 0 1 0, next level. So like that. So I will come back to why it is called MSB and LSB shortly. That will become clear to you when we understand how we convert digital to analog. So what are we studying now? This is analog. This is analog domain, okay. This is your analog domain. And anything left of this is your analog domain. This is your digital domain, correct. So here you have your digital bits, correct. So now we have converting from analog to digital. So we have set of bit sequences. So each of these bit sequences is called a digital word. So this is what you call a digital word, okay. Why it is called word? Why it is called digital word? Let us take your normal. So let me wipe it off. I will come back to what is MSB and LSB when I discuss what I told, digital to analog conversion. That time it will become very clear to you why it is called MSB and LSB, okay. So there is very thin line between, though you know that there is infinite levels in analog domain and there are very discrete levels in digital domain, but there is very thin line between the digital and analog space from a concept perspective. As I told, it is just two sides of the same coin, correct. So So, this is your analog and digital domain. I am just clearing the space so that it is visible to you. So, whatever bit sequence we are having, let us say 0 1 1 we take, this is called digital word. Okay. I want why we are covering these things like this is that we want also you to speak technically with confidence. Whatever word you use technically, you should know it fully, it should come out of you properly without any doubt, that gets reflected in the way you speak. And so, one more thing that we need to understand is that engineering education or even science education is not necessarily rotting up so many things, understanding so many things. It is also about transformation of your personal transformation into somebody who can speak strongly about the technological advancements that are happening in the world. For that, your base should be very strong and you should be well grounded in your technical concepts. Okay, this is just a slight deviation that I wanted to tell. So, that is why we wanted to tell you what exactly each thing means. So, this is called digital word. Why it is called digital word? Have you ever thought? I am sure that you would have heard about it somewhere, but why it is called digital word? It is very simple. Okay. So, now we have alphabets, right? A, B, C, D, E, that is your alphabets, correct? So, what is each alphabet called? Each alphabet is called a character, correct? But then when we join characters together, let us say we say car, what is this? What do we call this? We call this as a word, right? And each individual element has the character, whatever it is, this one, correct? So, here what is the base? Alphabet has 26 characters, right? So, that is your base. Okay. Same way, here what is your base? Your base is 2. What are your characters then? Your characters are only 2, either 0 or 1, correct? We are making a word out of those characters, that is this. So, you are forming your like you wrote car, correct? Like you wrote car, we are using the characters that we are available to us in the binary domain, which is 0 and 1, and make a word out of it. That is why we call it a digital word. It is a very simple concept, but it is very interesting how people when they, so all these concepts at some point in history had a beginning, right? Somebody sat down with a pen and paper and I thought, okay, let me introduce a new concept to the world. That time they would have used a word. So, there is another thing is that history is spoken only by the victors. Okay. History is written only by the victors. So, whoever finds the concept first or whoever makes the concept first, whatever word they use or whatever phrases they use, that gets stuck. And most of the time their selection of representations are usually good. So, nothing to complain, but then this is the way things proceed in our human history. Okay. So, this is digital word. It's understood, right? Why it is called digital word? So, it is like our characters are these and we are making a word out of it. So, we call it a digital word. Clear? Now, that is clear. So, now we have understood that we have an analog spectrum, correct? And we know what is our base is 2, and because to use our characters in the digital word to complete efficiency, we try to have multiple of 2 as the number of analog levels, okay, as a number of analog levels. So, then we understood that let us say if it is a 3-bit digital word. So, then now it is very clear to you to speak also, right? Now, what we call this, what we call it is, we call this as a 3-bit digital word. Okay. So, if it is a 3-bit digital word, you will have how many? You can have up to 2 raised to 3 equal to 8 voltage levels in your analog domain. It is not necessary that you need to have 8 levels, you can have lesser levels also, just that you won't be using all your bits with full efficiency. Let us say we have 4 bits 0, 1, 0, 0 something, that is 4-bit digital word. So, that will have that you can have how many levels in that? You can have 2 raised to 4 equal to 16 levels. same goes for higher number of bits, correct. Now you understood this, correct. Now you understood this properly. This is analog to digital conversion. Now let us say we have a digital word like this. How do we find out in reverse what was the analog level that it corresponded to? So this again I am reiterating, this is all this is like a practical course. So I am not going into the details of formula or anything, just intuitively we are just trying to see how, what is this, like with an image and basic concepts and all, just to understand, so that when you are making circuits, it all comes naturally to you, things should come naturally to you. Okay. So now we have a digital word, right. So how do I find out what is the analog value that this corresponds to? This is often that you need to see in your circuit design. Suddenly you will see a bit sequence, you need to see what is the actual analog voltage that this bit sequence corresponds to. What is it? What is the analog voltage this digital word corresponds to? Okay. This is the fundamental, why did I write this whole thing down? This is the fundamental question in, yes, you guessed it correct, digital to analog conversion, DAC. This is a fundamental question. Given that I have a digital word with me, how do I convert it into the corresponding analog voltage level in the given system? This is the fundamental technical question, the answer to which is your DAC. Okay. What is the analog voltage this digital word, which is this one, let us say 0 1 0, corresponds to? Clear? So let us see how we can answer this question. Once we answer this question, we already have our answer to the digital to analog converter, correct. For this, immediately you will think, you will tell me, most of you who are aware, you will immediately tell me that okay, 0 0 1, this is LSB, this is MSB. Now you start multiplying it with, adding and multiplying it with 0, 2 raised to 0, 2 raised to 1, 2 raised to 2, etc., and you will immediately tell me the analog voltage level, those who are aware of it. But then why each of these things is in such a way, that we need to understand. Okay. Then that will also give us the answer to why one digit is called least significant bit and the other digit is called most significant bit. Okay. So we have the bit sequence, correct. Let us say we take the bit sequence 0 1 1. Okay. Let us also write down the whole sequence of bits that this 3-bit digital word can take. So it can go from 0 0 0, 0 0 1, 0 1 0, 0 1 1, 1 0 0, 1 0 1, 1 1 0, 1 1 1, correct. Clear to you? Now if you observe this last column. What is happening? This bit is toggling at every change, correct. Every change it is becoming 0 1 0 1 like that. Okay, correct. What is there in this bit? It is changing only every other time, correct. For first two it is becoming 0, then for the next two it is becoming 1, correct. So what is the frequency of this? Frequency of this is, yes, every other, correct, and this is every 2 times. Let us say, so if we draw this as a what you call digital signal, like a time domain signal, it will be 0 1 0 1 0 1 0 1, correct. This is 1, this is 0, correct. If you look at it like this, 0 1 0 1, it is toggling. But what happened to this one? This guy is toggling with lesser frequency, correct. So, for first two, so when this is 1, this still remains as 0 as per this. So, this will be like this, then next time 2 times it is 1, correct. So, it will be like this, correct. Clear. So, let us say if this is 10 kilohertz, let us say this would be 5 kilohertz, correct frequency. Now, take the other one, this guy is not changing for first 4 words and then only changing once. So, basically it is having a transition only once, correct. If we draw that, how will that look? That would be for first 4 sequences it is 0, correct, and next 4 it is 1. Clear to you, correct. So, this is how these bits are changing, but then why are we looking at this? We need to understand how this can be translated to the analog voltage level, correct. Now, what these bits stand for is the information as to the level changes that happen right here. Each level change happens here, no. So, each bit is like having an information about these finer changes, okay. So, this last bit, right. So, that last bit like kind of tries to tell you that, okay, this is a major shift that happens, okay, and then these are finer additions to your voltage. It is like, let us say if you want to make 5 volt, okay, let us say you want to make 5 volt and you are trying to make it like this, 4 volt plus 1 volt plus 4 volt, okay. Let us say you are trying to make it like this, 5 volt you are trying to make like 3.5 volt plus 1 volt plus 0.5 volt, okay. So, this is the minor like finite change that happens in the addition. This is something intermediate and this is a major thing. This is same thing that happens here, okay. This is like a higher weightage in your each voltage level and this has a lower weightage, that is why it is changing every time, but a combination of these 3 bits gives you the exact analog voltage that is required, okay. Is it understood? Now, I think you are almost getting it, why each one is called least significant bit and the other is called most significant bit. So, because of this we understood, what did we understand, that if it is a we understood that if it is a 3 bit digital word, you will have 2 raised to 3 different levels, correct. So, this 3 is very significant, 2 raised to 3 levels, correct. So, then that is how you will convert this digital signal to analog. So, this is like the 0th bit, each bit is 0, 1, 2, clear, correct. That is how it is 3 levels. So, this is the 0th bit because it is changing every time, right, that is fine adjustment. So, that is 2 raised to 0, this is 2 raised to 1, this is 2 raised to 2, and in order to get the voltage level that it corresponds to, what we do, what we have to do is that, how did we come from the analog domain to the digital domain? We had a supply voltage, let us say VSS minus V0 which was 15 and 0 volt before, and we divided it into what, 3 levels, right. So, that is 8 levels, 2 raised to 3, correct. That gave you your analog this thing, what is it, analog interval value, correct. What is it, what is each interval value, correct. Then what we have to do, we have to find out what is the voltage corresponding to one level, correct. So, let us say we take 0 0, okay, that is clear to you, right. So, let me go back, let me clear this out. You understood what is digital word is. Okay. So, let us say we take 0 0 1, that is your second level that we know, because 0 0 0 is your first level. Now, we are doing 1 into 2 raised to 0 plus 0 into 2 raised to 1 plus 0 into 2 raised to 2, correct. So, look at the weight of each of these bits, weight of this bit is 0 or 2 raised to 0 was 1, this is 2, this is 4, this is this bit. So, it has a weight of 4 and the weighting value, the next one is the binary value, which is either 0 or 1. So, because of this higher weight, that is why it is called most significant bit, because it has the highest say in the analog value in your digital word. What is it? This bit, the most significant bit, has the highest contribution to the analog value of the analog voltage level of your digital word. It is clear to you? I will repeat it. Why is it called most significant bit? Because this bit has the highest contribution of analog voltage value to the analog voltage level of your digital word. That is why it is called most significant bit, and that is why this is called, yes, you guessed it, now you have understood, that is why this is called LSB. Clear? I had told you that I will tell you this concept when we discuss digital to analog conversion. So, I have kept my promise. So, we are doing digital to analog conversion, correct. So, now we have done this. So, what is this? What does this correspond to? 1 into 2 raised to 0 plus 0 into 2 raised to 1 plus 0 into 2 raised to 2 is what? 2 raised to 0 is what? 1, that is 1. But what we have to do? We have to multiply this with the analog voltage level in your system. What is analog voltage level in your system? Analog voltage level in your system is 15 minus 0 volt by 8. So, that is around how much? We had seen 1.98 around. So, 1.98 multiply equal to 1.98 volt. Clear? Let us take another digital word. Let us take another one. Let us say we take 1 1 0. How do we do that? Now, we know that this is LSB, this is MSB. Now, you know all the concept, why it has come like that. You do not have any doubts in your mind. If anybody asks you also, you can tell with full confidence why each one is what it is. So, this is 0 into 2 raised to 0 plus 1 into 2 raised to 1 plus 1 into 2 raised to 3, correct. So, that will be how much? 0 into 1 plus 1 into 2 plus 1 into 8, that is how much? 8 plus 2 10, correct. This is 0, that is 10, but 10 into what is your analog? What is that? Interval value, that is 1.98, okay. Not 1.98, sorry, So what did we get here? So 2 raised to 3. Yeah, so that's what. So what we have to do is that let's take let's take we have 111. Okay, what does 111 correspond to? 111 is 1 into 2 raised to 0 plus 1 into 2 raised to 1 plus 1 into 2 raised to 2, correct? So what is this? This is 1 plus 2 plus sorry, this is 2 raised to 2, that's why we made a mistake. This is not 1, right? We have seen, right? It is 2 raised to 2. When I was writing down I got a mistake. So this is 4, correct? So this is how much? So that was a mistake, please ignore that. So while I was trying to tell you about the 3 levels, this got messed up. So 0, 1, 2, so this is how much? 0 plus 2 plus 4, that is 6, correct? 6 into the interval value 1.98, correct? Roughly it's around 11.9 or 8 volt it will come, roughly 12 volt, correct? Let us say we take the maximum, though this should ideally correspond to what? This should ideally correspond to 15 volt, right? So this is two levels below, correct? Because in between what we have this is just one level below. We have 110 and then that is 111, correct? So 1 plus 2 plus 4 equal to 7, correct? 7 into 1.98, that will be around 13.98. So till there only. So whatever is above that value up to 15 volt, because we have seen, no, this is quantization, would be 111, clear? So your highest analog level would be the base of that, base of anything above that will be 111 up to 15 volt, correct? So this is 13.9 something, 98 volt, correct? Then we have below that 110. So like these things will be there. So this is how we have converted the digital word to its analog voltage level, correct? This is the whole idea of, see, I have not used any formula as such, we have just gone from intuition to intuition. So this just once we have just put 3 accidentally, that's why we got that mistake, but this is 2 raised to 2, and then we were able to get the analog levels very clearly, correct? This is the conceptual basis of digital to analog conversion. So there are a lot of circuits to do digital to analog conversion, and there are discrete ICs, correct? And we told you that this session we are trying to see the digital to analog conversion, DAC, we usually call it DAC. There are 2 types of DACs, please mind. There is one thing called DAQ, which is usually called, which is a data acquisition system. Okay, and then there is DAC, that also we call, many people call it DAC, that is digital to analog converter. Okay, so we have seen the concept necessarily how the digital word converts to the analog value, correct? And there are a lot of circuits which will be covered in the theory part of what are the circuits to do digital to analog conversion, correct? And there are also discrete ICs, integrated circuits that do this conversion, correct? So as we have told, so this module is to see the DAC module that is there in the ASLK kit that we have. We want to show you actually live experiment of how when we feed a digital word, what is the analog value you get. So the way I have covered it here is also in such a way that you can directly have a correlation with what you see in the experiment. Okay. So before we go into the board and see what it is, we have to know the circuit what they have implemented there. So it's not necessarily to know the circuit what they have implemented there. So there is one IC that they have used, which is the DAC 7821 IC, DAC 7821 IC, which is a Texas Instrument IC. There are a lot of integrated circuits that are available that do analog digital and digital to analog conversion. Okay. So what the IC that they have used in the board is DAC 7821. Okay. This IC is used in the board to do the digital to analog conversion. Okay. So you have an IC like this and it will convert digital to analog. Okay. So another main important thing before you try to see a circuit that is there is, because it is a very core IC and it does all the conversion, digital to analog conversion in the IC itself, you need to, before you look at any circuit that somebody else has made, because either you will make the circuit or you will try to use something, a PCB or a circuit that somebody else has made. Before you start using it, you should, because you are also an engineer and you are also a circuit designer, you should also go through the data sheet of whatever IC is used to understand. There are two things in that, why you have to go through the data sheets in detail. Always when you are designing, either when you are designing or when you are looking at somebody else's design, which both you will have to encounter in your professional career, you should be very careful that you should understand to the extent possible, because it is not possible to go through the data sheet of every single resistor, capacitor, ICs that are there in the circuit. You should try to understand at least the main components, the data sheet and how it is to be used. There are two main reasons why we tell this. First reason is so that you can use that component to its full potential, that is all its features can be exploited. Another more important thing, even if you do not exploit any features in the IC, you should make sure that you do not blow up the IC, please. Many of these ICs, it is not blow up, it is basically do not blow up. Do not blow up the IC. Sometimes it is beyond your reach, the power supply might have a fluctuation or your input voltage that you give might have a fluctuation, because of that IC might get damaged, but there should not be a technical shortcoming from your end, that you did not go through the data sheet in detail and you did not know that this pin we should have applied only this voltage to this pin, and we did not go through the data sheet, so we applied say 20 volt to that pin when I should have applied only 2 volt to the pin and the IC went bad. Many ICs are very costly, FPGAs and all are more than 2 lakh rupees one single FPGA. Some ICs are cheap, but we might not even know what is the price of these ICs, and we should not make that differential decision that okay, this IC is expensive, so let me go through it in full detail, and this IC is not that expensive, so it is okay if I blow it up. So that kind of attitude should not be there when you are a professional. So engineering education is a professional education, so this is part of your training to become a good professional. So you have to, the core idea is that, the fundamental idea is that you need to go through the data sheet and understand the basic things. So sometimes data sheets are like for 50, 100, 200 pages, and you will not have, fundamentally you will not have the time to go through everything in the data sheet. So next, before we go to see the kit as such, another important thing that we want to cover, because it's, again I am reiterating, this is a practical session. So fundamental in the practical section, one of the main thing is to understand how to use the data sheet in the shortest possible time, and how to best use of the, that's why companies make data sheets, right? That is for your own help, for your own use they make data sheets. So how to best use the data sheets, and use both its full features and all the precautions that you need to take care. So next what I will do is, I will run you through the data sheet of DAC 7821, tell you, keeping this as reference, keeping this IC as reference, what all things that you need to look at in a data sheet quickly, First we will go through the datasheet in detail, like kind of detail, not that much detail. Then I will do a quick recap and tell you suddenly if you have a new datasheet, what are the quick things that you need to look at in the datasheet before you go to either designing the circuit with that IC or analyzing a circuit that somebody else has designed. Okay, those are the two things that we will do before we actually go into seeing the how the board looks like and how we can apply inputs and see the output of the DAC. So this is kind of like slightly becoming a long module, but I guess you have understood the structured way in which we are trying to cover this. So first we have understood what is the basic concept of ADC, DAC, what is digital signal, what does it mean, without going into any formula or anything, basic concepts. Then we got into the actual practical aspect of it, okay, and we told you that there will be some IC that somebody will be using, correct, and then if given an IC, what you should do with the IC, what is the importance of looking through the data sheet, and now we will cover what exactly is there in this data sheet, that is just keeping the data sheet as a reference, and then how to quickly go through a data sheet if you have a new data sheet. Okay. Then we will see the board.